warm welcome, ladies and gentlemen. Today we are going to unveil a real revolution to the art and science of actuation. My name is Susanne Schöne, I'm a journalist and TV host, and it's my big pleasure to guide you through the upcoming approximately 45 minutes. So what's the plan for today? Well, first of all, we are going to introduce to you the company Metis Motion and have a quick look at the background story. And yes, we are going to explain to you why we need another electrical actuation technology. Then we deep dive more into the topic. We jump right into the technology platform naXture and see what's possible. And last but not least, there will be a live demonstration of the system's capabilities. But before we start, just one hint: if you have any questions, which would be awesome, please write us in the chat area. The team is going to answer as many questions as possible. Now, we are ready to start, and the first official thing I am allowed to do today is to welcome one of the founding members of Metis Motion, Patrick Fröse. Hello, Patrick, good to see you. So Patrick is going to tell us a bit more about the company itself and the whole background story. So Patrick, I will be honest with you, when I got your inquiry, you asked me if I want to host this event. The first thing I always do is to check the website. And there you promise a real revolution. And since then I was wondering, can a small drive system really make the world a better place?
Absolutely, thank you. I mean, movement and actuation is at the core of the creation of physical goods, but also of human interaction. I mean, looking at industry, it's pretty obvious when you create physical goods or you provide services, you need to move things around, you need to handle, you need to manipulate. But also when you look at communication between people, that is highly depending on movement. I mean, the body posture, the body language, gestures, that all requires movement, and we do that with muscles. We just don't call that actuators. Looking forward, I think we are facing a big revolution coming towards us. The revolution of the uprising autonomous systems, and that highly depends on two topics from my perspective. I think on the one hand, it's artificial intelligence. Can systems make sense of their environment? Can they understand what's happening around them? Can they make decisions? But then even more, secondly, once they've made a decision, they need to interact, they need to move. And that's actuation that is required. And in most cases, that is actually the big problem.
Okay, I think I get it. So actuation is key and challenge at the same time. So let's talk more about what's behind. Was or is that the real motivation behind Metis Motion?
Yeah, I think the recognition happened a while back when you realize the vast discrepancy between what technology can do and what humankind and nature shows us every day. I mean, the picture people have of technology is mostly Hollywood-inspired. Looking back into the 80s, there was Terminator moving very nicely. That was, I think, 1984 or something. But if we look at the DARPA Robotics Challenge 30 years later, that looks a bit dull. I mean, how far have we come? Not so far. So there is a big discrepancy between what we see in nature, between what we think autonomous systems need to be capable, and what technology really can provide. And I think that was the moment when we thought, okay, has the world come to peace with that status of technology, or do we need to do something? And I think, yeah, we set out to narrow that gap between what we see technically and what nature is showing us every day.
Yeah, I think we really need to talk about this robotic gap. I mean, just think of my hand, think of the human hand. I mean, I can handle a raw egg as well as, I don't know, a jackhammer for 8 hours. I can do that. Show me just one actuation technology that can do that.
It doesn't exist. I mean, exactly that's the point. It does not exist.
Okay, so that's so far very theoretical. So let's deep dive a little bit more. How did all of this start? How did it start with Metis Motion?
I think we have to look back a little bit towards the early 2000s. I mean, back in the day, driven by the automotive industry, that was very cost and qualitative sensitive back in the days, there was tons of research and development going on for solid-state actuators. That was used back in Siemens VDO at that time, but we took that more and more into the area of specialty actuator development. I mean, most compact, robust, dynamic, and efficient actuators you could think of.
Okay, talking about Siemens, don't we know Siemens more as a company for electromagnetic drive?
Absolutely, true, very true. But I think that helped because you quickly start realizing what are the strengths and what are also the limits of that technology.
What are the strengths and the limits? I mean, thinking about an electric drive on a highway makes sense to me.
That's perfect. Exactly the comfort zone of the electromagnetic drive. On the other hand, if you try to grasp a cup of coffee, that is exactly the opposite. So we pretty much focused on where are the limits of the existing electromagnetic drive technology and where are the areas that need solutions. And that's where the whole development then evolved. And in 2016, what happened then was the outside world caught wind of what's happening behind the curtains in Siemens, and they wanted to start purchasing products from us. The issue, as often in corporate research departments, you're not really in a position to sell goods to the outside world. And that was the time when we started discussing, okay, doesn't it make sense to set up Metis Motion as an independent company to serve that market need? Well, and now we're here launching the naXture platform.
Well, you just mentioned what's happening behind the curtain. We have you on stage, that's awesome. But what is behind the curtain? Tell us more about Metis Motion.
I think, first of all, there's a great team. I mean, of colleagues usually working with customers in implementing their specific actuation solutions. It usually starts with a very disbelieving customer. I mean, it's lovely. You have those very experienced, super highly skilled engineers that have been in their industries for a while. And the first thing you hear from them is, that's just not possible what you're promising. I can replace my pneumatic drive in the same space. I don't trust you. And then it takes a bit of collaboration along the way. You enter into co-development, you set up the specific solutions for the needs of your client and all the way down to serious manufacturing, which we're doing in-house.
That's perfect. And I would say let's have a closer look what this looks like in real life.
In the German technology metropolis of Munich, also known as Isar Valley, a new actuator technology has found its way to life. At Metis Motion, we provide customized actuators for your specific automation challenge. Your unique combination of standardized modules reliably provides the functions you need and can be easily integrated into your individual system. Our in-house development team covers the full cycle from mechanical design across power and control electronics development to systems integration and testing. Always with the appropriate attention for details. Where our experience and skills call for augmentation, state-of-the-art simulation and optimization tools ensure the highest performance levels for your application, even before proving our claims with our in-house prototyping capabilities. With a deep passion for details, a smooth transition into series manufacturing can be managed in the shortest time frames. Here, the best match between modern technology and the capabilities of experienced craftsmen brings your project to life. And if your application calls for specific interfaces, our software development team is here to help. Quality management is a matter of our engineering pride. This includes not only our product manufacturing, but also every sample on the way to your hands. So if you're looking for the right partner to unlock unprecedented capabilities in electrified high-force actuation, here we are. We are Metis Motion.
Oh, Patrick, that's super interesting. It sounds like you are having a very wide skill set in store for your customers.
Absolutely. I think you could rightfully call us a very knowledge-oriented organization. I mean, we don't really deal with rocket science in each of the individual steps we are looking at in our process chain, but I think the combination of a certain depth and quality in each of the required processes and steps we are integrating allows us to redefine what's possible in actuation.
So you were talking about all these processes. Do you cover all of them in-house or?
not as a general rule, but we are very conscious with regards to the processes that determine the quality or the functionality of our systems. Obviously, we collaborate a lot with the environment around us. There's universities for research activities, but also a very strong supplier base or a regional supplier base of partners that help us with products off the shelf, electronics components, or in areas where they have developed a very dedicated know-how to provide the products that we need. And that is specifically important for us. I mean, looking at the past year and supply chain security issues, I think having that local supply chain here helps us having a very sustainable approach to supply, but at the same time help our customers to scale very quickly and actually keep up with their demand for rapid growth.
Well, talking about customer growth plans, I mean, you are in a very early stage of your company, 14 employees. How can you handle all this? Or, I mean, better ask, what does it take for me as a customer to get my revolutionary actuation solution from Metis Motion right away?
And the answer is probably our highly scalable and modular naXture platform.
Tell us more about naXture, please.
Let's take a step back. I think we've to start a bit with the physics. Looking at the fundamental aspects of electromagnetic drives, they are very good in providing high forces across a wide speed range, right? We all have that picture in mind. But differently, if we look at a human muscle, the characteristics are fundamentally different. I mean, a human muscle can either provide a high force when it's not moving very fast, or it can move very fast without providing high forces. And take an example, we had the electric car that works very well on the highway, right? You want to accelerate at 120 kilometers an hour. Perfect for an electromagnetic drive. But if we look at grasping a cup of coffee in the morning, right? You want to approach it very fast. That doesn't take a lot of force. But by the time you've reached it, you want to hold on to it and securely hold it without spilling your coffee. That's a high force with limited velocity. And those are the 3 points in the graph we're actually seeing. Approaching very fast, point 1, then holding firmly onto at point 2. That's what the muscle can do very well. And on the other side, the electric car, it can accelerate on the highway still. We all enjoy that. That is point 3. What is important to realize is that the whole area under the curve is actually the power required. And we can easily understand that if we have applications in point 1 and 2, it's not a good idea to work with electromagnetic drives, because that whole unused area translates into unused copper and built-in inefficiencies. So your drives get bulky and heavy.
So what are examples for these, for 1 and 2?
Well, in industry, I think you easily find applications like grasping certain objects, clamping things, locking, unlocking things, positioning. Those are the classical areas we're looking at. But the graph at the same time shows the big issue when I want to use electromagnetic drives to resembling bionic behavior.
Okay, back to the topic. I mean, how does naXture address this issue?
I think in a first approximation, we can actually build a linear force-velocity characteristic that already gets us way closer to the characteristics of a muscle and reduces the power we need to install. And that's also the example we'll be presenting later on today. But even more interesting, by smartly combining the modules of naXture, we can build multi-stage systems. And if you look at the graph, you see that we're coming very, very close to the low power requirements we're having when we're looking at muscular tissues. And if we, for example, take this two-stage system, it's easy to reach forces of several kilonewtons, speeds in the range of several 10 millimeters per second, and all that with an electric power installed of, well, 20 watts or less, and you can hold it in your hand.
Perfect. So I would say, let's see what benefits arise from the naXture approach. Here we go.
naXture offers fully decentralized electric actuation and manages to save up to 75% energy compared to current state-of-the-art technology. It is fully metal encapsulated and builds on the strengths of microhydraulics, leading to extreme toughness. naXture provides the full force of a solid-state actuator in the smallest spaces and every step. naXture is your unique actuator based on standardized and qualified modules. How can this be possible?
Well, that brings me back to the question I have asked a couple of minutes ago. How is this possible? How can you provide every client with the exact solution he needs? I mean, we've heard that modularity is a great advantage, but how does that work?
I mean, naXture really helps us to really combine the specific set of functions and capabilities that the client needs in his specific application. And not as a new development project starting from scratch over and over again, but more of a smart combination of existing standardized qualified modules and linking those in an intelligent way. Let me try an analogy to phrase what I mean by that. I mean, if you look at electronics development and you want to implement a specific functionality in electronics today, you probably go to the shelf and you take capacitors, resistors, microcontrollers, transistors, whatever you need, and then you combine those on a printed circuit board, on a PCB. And by interconnecting those standardized components, you actually realize the specific functionality you want. Usually you wouldn't go back and start developing capacitors or anything alike. And naXture is very similar. I mean, we take standardized components and we find the smart and intelligent interconnection or link between those components to implement the functionality the customer needs.
So is that what you meant when talking about unlocking the new skills? Or?
Exactly,
okay.
Exactly. I mean, usually a project starts with really defining the required functionality, right? I mean, there's the basic topics like what kind of forces are required, what velocity do I need, what stroke does need to be implemented. But then quickly you also get into topics like required safety behavior. If you're coming from hydraulics or pneumatics, fail-safe behavior such as normally open, normally close is totally natural to you, but that doesn't really work well in electrified systems anymore. So that's a big topic for many customers. Beyond that, there is specific requirements for dynamic capabilities, like control bandwidth, specific accuracy requirements, always depending on what the customer wants. But then it often comes back to the point where you think of how do we best integrate that in the existing design space the customer application brings. More thinking about robotics and advanced applications, there is in addition topics like inertia. How do we reduce the inertia on our output? How do we actually make the impedance adjustable? And what's really cool about naXture is we simply draw from the standard modules and we can implement that very fast and cost effectively.
Patrick, that sounds awesome. Thank you very much for being with us today and for sharing all these insights. Thanks a lot to you. And you, ladies and gentlemen, are now probably wondering, what are these standard modules? I would say, let's have a closer look.
Our naXture solution kit comprises different standardized modules. The electro-hydraulic converter. This highly integrated module is the core of every naXture actuator. Powered electrically and easily controllable, it provides the necessary forces and movement. Our fluid control unit. Here, passive switching elements are used to configure functions such as the safe state as well as the dynamic properties of the system. The hydromechanical converter. This is the interface to your system. It can be flexibly designed, from mechanical power extraction to direct hydraulic integration. The required forces, speed, and stroke can be easily adjusted. They all come together in the most suitable arrangement for your actuation task. The smart housing, serving as the central nervous system of the actuator and connecting the modules into your unique solution. With our disruptive naXture technology, we open up the possibility for you to excite your customers with real, previously unimaginable innovation. Are you in?
So, as I have promised you in the very beginning, we are now going to deep dive more into the topic and have a closer look at the platform itself. And again, if you have any further questions, please feel free to use our chat function during the whole event. Now, it's time to welcome the next founding member of Metis Motion, Wolfgang Zölz. Wolfgang, it's a pleasure to have you.
Thank you.
So Wolfgang, you are responsible for the manufacturing and the standardization of the modules, and you are going to tell us a bit more about the underlying technology. But before we have a closer look into the modules, you need to tell us, how does the system actually work?
Well, we took our inspiration from nature, especially in the muscular tissue. So basically, a muscle adds up strong micromovements and thus creates longer strokes. So we have a similar principle, but instead of the muscle, we use our electrohydraulic converter here, which is based on a strong solid-state actuator. So this is driven by the electronics with a high frequency.
And that means these are also tiny little micro movements that are added up here like a muscle does.
Exactly. We use highly integrated fluidic circuits to add up these micro movements. So with this, we get longer strokes with extremely good controllability, high forces, and also low virtual inertia. So for example, we can easily apply more than 1,000 newtons with these small components.
That's really crazy. So if I got that right, the electrohydraulic converter is the only active module in the system, right?
Yes, that's a very important aspect of naXture. So we have robust actuators due to the absence of active components besides this electrohydraulic converter. So with the combination with the passive modules here, we can apply easily different states and functions without complex control. So it's possible to have a soft or stiff function, also a force retraining here.
Okay, but how have the modules to be integrated in a customer design space? Is there any sequence?
Well, we have a high flexibility here. The only requirements are the right fluidic connections between the modules. So since the fluid do not care about flowing around any corner, we can integrate it optimal into the design space of the customer, in contrast to mechanical connections, which are typically used or required for other technologies. But maybe we can visualize that with an example. So in the following animation, you will see a swing clamp, which is a hydraulic device used for clamping. So for this, you need additional external components like a tank, pipes, and a pump. If you want to electrify this, the size of the swing clamp will increase significantly. So let's see how naXture would work here. As we can see, our components easily fit into the existing design space. This is the most simple configuration with the active actuation in one direction and a passive reset. With this setup, we can get a maximum force of 2 kilonewtons and a maximum velocity of 10 millimeters per second. In the second version, the implementation of different impedance characteristics is done. In this case, only a changed electrical control signal is needed, as illustrated in the block diagram. The change of impedance will be also shown more in detail in our demonstration later.
So as you have seen in the example, you can easily integrate the modules into the design space of an hydraulic swing clamp, which is much smaller than an available electric version, right?
That's right. And in addition, we can get rid of all the components around the swing clamp, such as the tank, the pump, and the pipes.
Okay, and the modularity of the system allows to adapt the actuation performance to the customer's requirements, right?
Yeah, that's right. We can use this example as we have seen before. So here we had a maximum force of 2 kilonewtons and a maximum velocity of 10 millimeters per second. So if a customer wants to have a higher force, we can easily adjust the output piston or the diameter of the output piston of the standardized hydromechanical converter. So with an increase of about 25%, we get about 3 kilonewtons and a maximum velocity of about 7 millimeters per second.
Okay, and do you need more design space for that change?
Well, that's a good thing. The design space as well as the interfaces keeps the same. So it's a one-by-one exchange of different versions of this hydromechanical converter.
So why is the velocity decreasing here?
Well, since we still have the same electrohydraulic converter and therefore the same mechanical power, an increase of force is always linked with a decrease of velocity, or the other way around. So these are physical limitations here. However, there are much more possibilities of combining these standardized modules here. For example, for extending the force-velocity characteristics, or for enabling a bidirectional actuation, also allowing a different fail-safe modes. Adding a second electrohydraulic converter and fluid control unit, a bidirectional actuation system can be realized, so the system can be driven actively in both directions. The next configuration is a similar bidirectional actuator, but with normally stay behavior, since no spring reset is implemented. For this, another version of the fluid control unit and the hydromechanical converter is used, as illustrated in the block diagram. The last example is a battery-driven setup. Due to the high efficiency and low power requirements, much longer battery-driven operations are possible compared to other electric drives.
Okay, interesting. That means you can also adapt the fail-safe behavior in case of electrical power losses.
Yeah, that's right. As shown in the diagram, we can easily change the design between different fail-safe modes. So, for example, normally open, which means that the actuator moves back to minimum position, or normally closed, where the actuator moves to the maximum position, or normally stay, where the actuator stays in the last position.
And can't that be done similar with other actuators? Or?
Well, that's possible for other fluid actuation technologies. But if you want to have electric drive, it is very difficult due to the typical combination with gearboxes. So here, our naXture platform has a big benefit for our customers.
So Wolfgang, what surprised me here the most is that you are using a second electrohydraulic converter. What's the reason? Why is that?
Well, one possibility could be that the power is not sufficient. So with a second pump, you can double it.
So for the increase of the force and the velocity?
Yeah, that's right. But you can also use the two pumps for bidirectional actuation, as we have seen before. So that means one pump for the extension and one pump for the retraction.
So that you have the same high force and velocity for both directions.
Exactly. But if a customer wants to have different characteristics, so for example, a high force for the extension and a high velocity for the retraction, that is also possible.
Okay, are there any further possibilities here?
Well, we can also use the two pumps for nonlinear force-velocity characteristics as the muscle do.
Please, you need to explain that for us a bit more in detail, I think.
Well, of course. Well, we can combine similar like before, two pumps. So for example, one pump with a high force and one pump with a high velocity. So by this, we get a two-stage force-velocity characteristics, as Patrick showed at the beginning, which is similar to the human muscle. So with this, we have a working point with a high force and also a working point with a high velocity. And this with very low power, since the integrated area under the curve is very small. However, there are also more possibilities of combining these modules in order to fulfill the requirements for our customers.
Wolfgang, thank you very much for all these insights. We've heard a lot about the potential possibilities, a lot of theory. I think it's now time to look into the practical stuff and to look at our live demonstration. And therefore, it's time to introduce the third founding member of Metis Motion, Georg Bachmeier. Georg, it's a pleasure to have you.
It's also a pleasure for me to meet you.
So Georg, you are developing actuators for more than 20 years now, and you are responsible for the R&D activities of Metis Motion today. So we already talked a lot about the naXture platform, and I think we all can't wait to see it in action now. So what we've also learned is that there are plenty of configuration options. So what are you going to present to us today?
For the demonstration, we choose a very simple configuration. We see it here. We have only one electro-hydraulic converter. We have two fluid control elements inside, and we have a hydraulic mechanic converter with a reset spring inside. And this is all in this housing made by stainless steel, and we have one without control electronics and one with the integrated control electronics. So converter is responsible for one direction and the return spring for another direction. This is similar to our muscle. We have an agonist and we have the antagonist. The agonist in this case is the converter, the active part, and the passive part, the spring, is the antagonist.
Okay, so can you tell us a bit more about the technical details and the performance of this specific unit?
In this case, is a really good balance between force and speed. The maximum force is in the range from 1000 Newton, and the maximum speed in the range from 10 millimeter per second. And the weight from the system is approximately 300 grams.
Okay, so considering the weight and the compactness of the system, that is quite impressive. So, but what triggers my curiosity even more is your claim, the new generation of nature-inspired actuators. Can you tell us more about that?
Of course. The claim revels the inherent properties of this actuator.
Such as?
For example, the ingenuity of our hand is that it is possible to grip an egg, also to move very heavy weights, or works over hours with a jackhammer. And why is this possible? The key is that the muscle can change the impedance, the stiffness, by controlling the agonist and the antagonist. And this functionality of the muscle, we do it in the same way with our actuator.
Why is that capability so important for actuators, other than for muscles, for example?
Classical systems, motor with a gearbox, normally designed to be stiff as possible. Why? This helps to improve the accuracy from the systems, and also to eliminate oscillation and so on. But for specific application, that sensors and closed-loop control systems decreased the stiffness of the complete systems. But the delay from the controller, or also the maximum performance from the actuator, the maximum power, limited the range from the impedance. For example, in a case of a collision, that you get an overload and the system is not able to react in the right way on this collision. And therefore, there are many activities on the field of research activities, and there, for example, is various stiffness actuator or various impedance actuator. And this all exactly the intrinsic properties from our actuator.
Okay, it sounds good. But as we all know, there are always two sides to a medal. So are there any disadvantages compared to the stiff actuators?
None. In the field of low power actuator, there is, I cannot name any. Why the naXture bring all the necessary characteristics for a wide range of application. But I think let's start to look at the system in action.
Absolutely, we can't wait. Okay, Georg, so what have you prepared for us today?
A very simple test bench. You can see here, this is only with remote electronics, and in this plug you see we have 2 pins. This is for our converter, and we have a small program inside, then we can move our actuator with 2 different speeds, first a slow one and then a fast one. Now, second try. Okay.
Okay, that was a little bit impressive. Georg, let's now talk about the even more exciting characteristics. For example, the intrinsic variable impedance. Can you demonstrate that as well?
Yes. Let's take our example, the raw egg. Now, I will increase the test bench a little bit for a plate. And now we see we have here a blind tip. And here nearly a surface. And now we try, the system is stiff. We have no sensor, no force sensor, no position sensor, only inside a lookup table where we can preset the force and the impedance from the systems. Now we will try to clamp this egg between the tip and the plate. The relatively high clamping speed is only possible because the inertia, the reflected inertia from the naXture actuator is really low. You know it, for example, from your breakfast egg. When you have only a small impact with your spoon, the shell breaks. And this is the low inertia is really a key feature for all grasping and clamping application with sensitive parts.
Okay, Georg, that was already very impressive. At the very beginning, you maybe think about it, I mentioned that the human hand is like really unique. We can handle the egg as well as a jackhammer. So obviously you can do the egg thing. Now I'm wondering, what about the jackhammer?
Okay, I will show you. Max, can you help me for a moment?
Well, that's obviously a job for 2 men. Wonderful.
Now, we will lift this barbell. The weight is 40 kilograms.
Wow, okay.
And now we will lift it in 10 millimeters in 1 second, and then it's dropped down back very fast.
Okay, that looks very heavy, but how does that compare to my jackhammer?
Yes, the impact energy is in the range from 4 joule. The impulse is 14 Newton seconds. This is a typical value for a jackhammer.
Okay.
And now you will see. It's your time.
Okay, Georg, so why can this actuator do this and others cannot?
The reason is simple. A gear motor, for example, have form closure elements inside. The contact area are very small, and in the case of collision, for example, you get the overload, and these elements are not able to transmit this force, and the tooth breaks. In hydraulic systems, you have the fluids, and the fluids are able to transmit the forces or the impact perfect to the complete surface. And also the damping effect from the hydraulic fluids that you have can filter the high frequency parts.
Okay, and another important question, I think, I mean, under such loads, is the system still precise?
I will show you
okay.
the preciseness of the systems. I will extend the test bench a little bit.
Okay,
This is measurement device, and now you can see the speed and the position, and we will try to move it in different directions, different speeds, and hold one position. Now I will start.
Okay, so how much power does the actuator now need in operation?
It depends from the application. For this 40 kilogram, to move with the maximum speed, you need nearly 20 watts. For clamping an egg, this is less than 1 watt. The range is between 1 watt and 20 watts.
Okay, so in this case, the hydromechanical converter is a linear element, but is it still flexible?
Wolfgang have shown one example with a clamping device that you have a spiral movement. And it's also possible to get a rotation movement, or with free-form cavities inside, you are really able to get each movement what you will have. The options are nearly endless.
The options are nearly endless. Georg, thank you very much for sharing all of that with us, for all the presentation. I think that was really impressive and exciting to see for all of us. Georg, thanks a lot.
Very welcome.
Well, can a small actuator system make the world really a better place? I've learned a lot today about the role of actuation in our day-to-day life. And I've also learned that there are plenty of limits with the current technologies that we have. naXture is efficient, decentral, robust, precise, dynamic, and can be made perfectly fit for your requirements. I'm sure you still have some questions left, and that is good because our team is going to stay around in the chat for a bit longer. And even if your questions pop up later on, don't worry. Of course, you can contact them at any time via email or telephone. And make sure to check out the new website. You will find plenty of information there as well. Thank you very much for your time from my side, and all the best to you.